When you vibrate a flat metal plate covered in fine sand, the particles don't bounce randomly. Acoustic waves force the sand to organize into precise geometric starbursts. This is known as cymatics, the visual shape of sound. Look at the center of this instrument, cast 2,600 years ago. The identical geometric starburst and concentric waves are permanently etched into the bronze. This is a Dong Son drum. Around 600 BCE in modern Vietnam, metallurgists engineered these massive, highly resonant instruments. The resemblance between these ancient engravings and modern cymatic patterns presents a compelling historical puzzle. It raises the question, did the artisans who cast these drums physically observe the geometry of sound as they worked? If these patterns were derived from actual observation, it means early humans mapped the physics of acoustics thousands of years before the development of formal scientific methodology. The Dong Song drums were an impressive engineering feat, but they did not happen in isolation. Across Eurasia, the period around 600 BCE saw a simultaneous surge in the creation of resonant metal instruments. In the West, uncontacted ancient Greek and Celtic societies were forging large bronze objects specifically designed for their acoustic properties in sacred ceremonies. At the exact same time in Asia, metalworkers were casting massive bronze drums and thick bossed gongs capable of producing deep carrying frequencies. We have no archaeological evidence of direct communication between these hemispheres during this era, yet both sides of the globe independently discovered that heavy cast bronze could transform physical vibration into powerful acoustic energy. This parallel development suggests these cultures were not necessarily trading specific regional ideas, but were instead independently discovering and applying universal physical laws of resonance. Many archaeologists argue that the wave-like geometries on instruments like the Dongson drums are purely symbolic. They are often interpreted as solar motifs or astronomical maps that simply happen to mimic modern physics diagrams. However, acoustic research points to active engineering rather than mere decoration. Studies on similar ancient Chinese bronze drums reveal specific fan-shaped structures cast into the interior of the metal, explicitly designed to diffuse sound waves and increase resonance. This acoustic mastery is clear in the Bianzhong bell systems. These multi-tiered instruments demonstrate a sophisticated grasp of harmonic physics. A single bell produces two distinct notes depending on where it's struck, controlling wave propagation through the metal's physical shape. This structural engineering evolved from earlier bronze instruments, like the now bells, where makers added protruding studs and precise geometric patterns to physically alter how the surface vibrated. Because we know these early metallurgists were intentionally manipulating internal sound wave diffusion, the idea that they noticed and utilized the visible patterns created by those vibrations is physically plausible. The formal science of visible sound didn't emerge until the 18th century. German physicist Ernst Chladni demonstrated that when a plate vibrates, sand sprinkled on top will physically move away from the vibrating areas and settle along stationary boundaries called nodal lines. Chladni pattern analysis provided a reliable way to map the stiffness, flexibility, and overall resonance behavior of any flat surface without needing complex modern electronics. Today, this centuries-old acoustic science is still put into practice. Master luthiers rely on these visible geometric patterns to physically build and tune the soundboards of world-class stringed instruments. The technique is known as plate tuning. A maker carves a raw piece of spruce, sprinkles sand across it, and applies a vibration to reveal the structural modes hidden inside the wood. This animated diagram shows how frequency changes as the mass of the wood decreases. By shaving away microscopic layers, the luthier reduces mass, directly shifting the geometric sand patterns until the wood achieves perfect resonance, often targeting a specific shape known as mode 5. Tuning a violin through visible geometry is a highly effective, physically necessary method for perfecting a resonant acoustic instrument. The physical requirements driving the wooden top of a modern violin mirror those driving the bronze face of a 2,600-year-old drum. Both require a precisely tuned surface to project sound. We cannot definitively prove that ancient metallurgists intentionally used sand or dust to map out the nodal lines on their instruments, but the precision of the physical resonance they achieved is an undeniable acoustic fact. Whether they were guided by particles dancing on a ringing drumhead or by a deep cultural intuition about geometry, these early artisans tapped into the exact same acoustic principles as a Stradivarius maker. The mechanics of vibration are constant across time and material. The mathematical equations governing the resonance of cast bronze are identical to those shaping carved wood. Sound is an invisible geometric structure. Recognizing and harnessing that structure has driven human engineering, art, and connection since the Bronze Age. To continue exploring the deep connections between music, science, and history, visit the Diapason Global Education for Music at dgem.org.